Good afternoon, everybody, and thank you for joining us today. This is part 3 in Arista's Next Generation Service Provider webinar. And today we'll be taking you through some next-gen service provider use cases. And in just a second, I'll be handing over to my colleagues, Florian, Yaroslav, and David, to take you through today's presentation. Just a quick piece of housekeeping. If you have questions, please do ask them. But if you could ask in the Q&A window, not the chat window, that would be appreciated. We'll only be able to answer questions in the Q&A. So without further ado, I'll hand over to the guys to take you through today's material. Thanks very much.
Thank you very much, James. So let's take a look at today's agenda. We have a number of exciting next generation SP use cases for you today. First of all, we will look at a new EOS innovation known as Routing Control Functions, or RCF. After that, Florian will be taking you through some routing security with RPKI, and then Yaro will take you through some traffic engineering using segment routing. We'll then take a look at applications of BGP flow specification or flow spec, and then Florian will take us through some next generation IXP architectures. But before we get going, I'd just like to quickly refresh you on the really foundations we have for service provider routing at Arista. And of course, combining our extensible operating system EOS with really the latest in merchant silicon. And if we take a look at the legacy routing market, traditionally vendors have used their own custom routing silicon, and that's primarily been because of the complexity of functionality that service providers require, and also the scale requirements that come with that. But there are a number of challenges around that. Often we may need to add service blades. Port density is often compromised with that custom silicon, and that results in quite a high legacy price per gigabit. And so with the latest merchant silicon, those lines are really blurring in terms of the routing features that are available on merchant silicon, but also the table scale as well. And if we look at the latest generation of chipsets, we actually have very high capacity, both in terms of table scale and in terms of bandwidth. And the primary means of that for the service provider market to us is our R series of routing products. And that is comprised of the 7280, the 7500, and 7800 R series, the latest generation of which you can see on screen now, which is the R3 series. And of course, all of those common Arista EOS benefits still apply. So we still have that single binary image across all platforms with consistent silicon throughout the R series. And that silicon has deep packet buffers and virtual output queues for a truly lossless architecture. It also has very large table sizes as demanded for example, for internet scale routing. And within that portfolio, there's quite a wide variety of form factors, density, port speeds, going from 1 gigabit all the way up to very high density 400 gigabits, depending on the use case. So taking that as really the foundation, let's take a look at some practical use cases that we can run on that portfolio. So the first I'd like to take you through this afternoon is known as Routing Control Functions, or RCF. And this is really a next generation means of routing policy control that we've just released on Arista EOS. So first, a little bit of background as to why this is needed. Well, many of you today will manage your routing policy primarily using route maps. And this is a technology that has been around for many, many years now. However, depending on the use case, there can be some challenges around using route maps. There can be a lack of flexibility depending on the routing policy you wish to apply. And part of that is because route maps are very linear. So you need to define this in a very rigid sequence. And you can add some flexibility using nested or sub route maps. So that's using continue statements and so on. But that's still not very flexible. And this can actually become very complex. And if you're trying to define quite a lengthy routing policy, these route maps can quickly run into the hundreds and thousands of lines and become very difficult to manage. And so announcing our new technology, routing control functions, or RCF, this is a much more flexible means of defining your route policy, essentially as code. And so for those of you with a background in programming languages, it will seem much more familiar to you than the traditional rigid route map approach. And so with this, we've effectively designed a new language that you can program with AOS. And within that language, you can actually have a much more flexible, much more granular routing policy. So for example, the sort of things you typically do with routing policy, such as route filtering and routing attribute modification, you can do within this new language with a lot more flexibility. So as mentioned, this is a new technology, and this is actually shipping today from our latest EOS software release, which is currently 4.24.1F. So let's take a look in a little bit more detail. As mentioned, RCF is code. And so like any other code and any other programming language, you can choose to write this off box, perhaps in your text editor of choice. And once you have that, EOS devices can retrieve that remotely from those external sources. So for example, you might want to have it in some sort of version control, such as Git, and then the local EOS devices can retrieve that configuration, automatically compile that config into their CLI pending buffer, and then, assuming you choose to, commit that to the running config, at which point that code becomes part of the running config. Now in this diagram here, you can see it as being quite linear, but you could also imagine that this running config could go back into your version control, completing the loop there. So, as mentioned, it does look like a programming language, and so those of you with a background in that will see a lot of familiarity here. Within our RCF code, we can define functions, and each function can perform some sort of task before returning a value. So that value is typically true or false, but it can also return unknown, depending on the use case. Now, once we have defined a function, that function can be referenced in other functions. So straight away, you can see that you're getting a lot more flexibility in how you define your policy compared to, say, a route map. Now, within our functions, we can then use logical expressions in the way you would expect in a normal programming language. So for example, we could do comparisons. We could compare a given prefix against a single prefix, or we could compare it against a prefix list. We can do match operations, so assignment. So in this example here, I'm using a variable, in this case called local preference, and assigning it a value of 200. And we can do assignment and increment and decrement here as well. Now, the cool thing about this is it's actually modifying the modified or intermediate state. So the local preference may start out at 200, and depending on the programmatic nature of our code, we can vary and manipulate that along the way. Let's take a look at a quick example here. Now, once this is committed to the running config, we have this text code at the top, and that denotes the start of our RCF syntax. Then we have our function definition, which is defined with a function name and the opened and closed brackets. And then we have the return value as mentioned, and that could be using a comparison, as we can see here. So for example, if the origin of our route is our IGP, then we will return true. Otherwise, we will return false or possibly unknown. As mentioned, we can assign variables. So in this case, we're using the multi-exit discriminator, or MED, and we're assigning that the value of 100, and then performing some comparison and programmatic either increment or decrement of that MED value before returning true. Now, once we've compiled all of our functions, when it gets committed to the running config, as you will see shortly, we have the EOF text just to denote the end of that syntax. So that's great to see it on a slide, but I think the better way is to see a quick live demo of that. So let me show you that now. So for a very quick demo, here's a router that I have in the lab running that latest version of software as mentioned. So if I do a show version, we can see here that this device is running EOS 4.24.1. As it happens, it's a 7280 R series, but this RCF feature I'm showing you here is actually a platform independent feature. Now, in my lab, in my small environment, I have some BGP peerings that are running. So if we look at the configuration very quickly, we can see here that we have a number of BGP peers configured. And if we look at our BGP table, we are receiving some prefixes from each of those peers. In this case, it's a very small BGP table, but naturally all of the principles you're seeing could apply to much, much larger scale as well. So we can see here we're receiving the routes from each peer and their various metrics, local preference, weight, AS path, and so on. Now, with RCF, we can use our code to manipulate this routing policy. And so the way this is performed is using, if I enter configuration mode, we can then go to router general. And if I run question mark here, you can see we have a new section, which is control functions. And so it's in this configuration mode that we're going to add or remove our code. And so if I go to control functions, you can see there's a number of options here to add or remove our code. So our typical means of pulling it from, say, version control would be using the pull command here. And so if I run question mark again, you can see there's quite a wide variety of sources we could retrieve our RCF code from. So that could be from secure copy, SCP, it could be from HTTP or HTTPS, or a number of other options. Now in my example, just for the demo purposes, I'm actually using my text editor of choice on the local box, which is VI. And so using the bash command, I can actually access any of those underlying Linux features within EOS. And so I'm going to choose VI and go to edit my code. So file on the flash, I've just got a small text file here, and you can see that we have a small example of some RCF code here. In this case, I have a function at the top defined is default, and this is a function intended to return true if the prefix is a default route. Now, this is true whether it's a IPv4 or an IPv6 prefix. And as it happens, I've commented that out. So we can add comments into our code using this hash function just for demo purposes, and we will come back to this later. So once we've written our code in our editor of choice, we can then pull that into the local configuration. So using the pull command, I can specify my location. In this case, it's on the flash and the file name. So once I hit enter now, we're going to retrieve that configuration and automatically compile it into the switch or router's CLI pending buffer. Now, as it happens, this is still not taking effect, and so we do need to commit it once we want to commit that to the local running config. So once we've done that, we can access some show commands, including show BGP. We have a new command, show BGP RCF. And here we can see that we have now activated those three functions defined in our code as part of our running config. So let's apply this policy and use one of the functions somewhere. So if I go into BGP configuration mode here, we can then use this policy either in the IPv4 or IPv6 address family. In my case, I'm going to use the v4 address family. And so now when we go to define our neighbor statement, we can actually see that we have the option to specify RCF functions. And in this case, I'm going to apply it inbound, and I'm going to use my local pref modify function. So once that is configured, this policy is now applied to the first of my 4 BGP neighbors. So if I run show IP BGP and look at the routes we're receiving, well, we have no modification changes to the local pref yet. Well, why is that? Well, it so happens there's actually that small mistake in my code. So you can see here that I'd commented out the function that actually matched whether we had a default route. And so that function is always returning false. And this is the function that is referenced in my local pref modify function. So if I were to comment that out as follows, then we will need to, of course, recompile that code. So if I go back into the configuration mode, router general, control functions, we can then pull that code again. And if I run that again, we will see still no change. However, what do we miss? We still needed to commit that code. And so once that code has committed, that routing policy can be processed in real time. And you can see straight away that we have programmatically manipulated the local preference of this default route for this given peer. And it has now been assigned a value of 299 as per our code. So I hope that was a good, quick overview of routing control functions, and look forward to seeing you use this in your network. Next, I'd like to hand over to Florian, who's going to take you through some routing security. Over to you, Florian.
Thank you, David. Yeah, I would like to tell you a bit about routing security with RPKI. And therefore, I would like to give you a small overview what RPKI actually does, what it is for, and what it consists of. So first of all, RPKI has been invented to prevent misconfiguration or intentional hijacking of announcements of IP prefixes from non-validated AS numbers inside the global internet. As several incidents have shown in the past, those hijacking of prefixes can lead to traffic being either redirected to a bad target, or even just to black hole, and therefore kind of denial of service a given prefix. The solution here, RPKI listed as RFC 6480, allows an internet number resource, namely an AS number and an IP prefix, to be associated with an authoritative entity, which can be something like RIPE, ARIN, APNIC, AFRINIC. They hold so-called trust anchors. So RPKI actually kind of consists of two parts. First of all, the resource holder signing their resources with certificates via the RIRs, and service providers acting on RPKI validity with accepting, rejecting the routes, or manipulating the route state. Next slide, please. But let's talk a bit about the terminology inside of RPKI. RPKI needs so-called ROAs, Route Origin Authorizations, which is a data set of prefixes, AS numbers, and a so-called max prefix length in conjunction with an authentication which comes from the Regional Internet Registry CA, a match in the RIR resource database, and the resource holder creating this ROA and therefore authenticating it. Those ROAs are then stored in a global repository owned by the RIRs and can be obtained via rsync mechanisms through local cache servers sitting on your network. For the communication between those local cache servers, which are running all the cryptographic operations and the cryptographic validation of those ROAs, there is the RTR protocol, RPKI to router. So as the name already says, it's spoken between the local cache inside of your network and the router itself, and is exchanging the already validated prefix information between those two entities. Next slide, please. So what is it then, or how is the whole workflow going? So you're setting up your own RPKI caches, or preferably multiple of them, running different software just in case you're hitting a bug or anything. Those caches are syncing the ROAs from the global RIR repositories. There are several cache servers currently out there, namely the RIBE-NCC Validator, Routeinator, and OctoRPKI, just to name the most famous ones. The cache then validates the ROAs and will exchange this information via the RTR protocol with the routers. When the router itself now receives BGP updates from its peers, it's able to validate those prefixes using either the cache information it has received via the RTR protocol, or by using the origin validation state extended community, which can be attached to the received routes and is usually used with IBGP. Afterwards, by applying a route map or anything, you can act on the validation state. So it is completely up to you what you would do with the validation itself. Now, next slide, please. Now we can have a look at a live demo and how RPKI would look on a EOS system. So in this demo, I'm having three RPKI caches set up. I do have a router on the right side. The caches speak RTR with the router, and the router itself holds a BGP full table. On the right side, we see the configuration, what I'm doing. I have an inbound route map, which permits non-found ROAs. That means accept prefixes for where ROAs haven't been issued. We're denying invalid prefixes or prefixes with an invalid ROA entry, and we're permitting valid ones. In the router BGP section, we do see the configuration of the three RPKI caches. And then probably the most important piece of configuration, the RPKI origin validation, which tells the system how to act on the different types of BGP. So for eBGP, we want to use the local caches inside of the network for validation. For IBGP, we prefer the origin validation state community if it is attached, otherwise fall back to the cache. And for outbound IBGP members, we want to attach the extended community I just mentioned. So now I would jump on my demo system and give you a quick glimpse. So what you see right now is essentially the setup I've just shown you. And we have a look at our BGP neighbor table. We see we're receiving about 819,000 prefixes. So route map is configured as we just shown on the slide. And the BGP configuration is also there. We see here the RPKI origin validation. We see the three caches. And we see that we have the route map attached to the neighbor. So now let's have a look if the caches are connected. So we retrieve the information for the RPKI caches. We see the state is synced. connection is active. And most important, if you bring down a cache for maintenance because you want to upgrade the cache software also on a regular basis, we also have the expiry interval so that you don't lose the ROA data in case you just want to restart the software. So also now let's see how many ROAs we're actually receiving. 138,014 ROAs are in the local database. And as you can see, it's varying here a bit. So that means one cache is slightly ahead of the other one. And the total data is being merged up in the global, in the local cache. So how does a ROA look like? As I stated to you before, it essentially contains three informations. It does contain the prefix itself, a max prefix length, and the ASN, which is allowed to advertise this prefix. So now we've had a look at the RPKI information, but how does it actually look inside of BGP? This output is probably very familiar to you, but now a new tag has been added, the AS origin valid. So you can have three states here, as I mentioned before: valid, invalid, or not found. So also, as we're dropping invalid prefixes, or prefixes with an invalid ROA to be very precise, let's have a look how many prefixes are there and how do they look like. Those are all filtered on ingress. So those prefixes I actually drop. And it's denominated by an I here, which is also additional information in the show IP BGP output. So you can see up here that we have the three codes: valid, invalid, and unknown, and it's denominated here. So if we have a look, how many prefixes are we filtering right now? They might be hijacked, misconfigured, or anything like that. So we're protecting our network currently from about 4,029 invalid prefixes, which could do harm to our end users. Therefore, I would like to end the demo and hand over to my colleague Jaroslav.
Okay, well, congratulations, Florian. I know live demos are not easy. I have completely different subject though. Let me start with the short problem statement. We all know dynamic routing protocols are calculating paths hop by hop. Specifically, BGP algorithm is very flexible, but even though we are not always happy with the best path proposed, often we would like to add some more parameters to the equation, like setting better, cheaper transit provider, or maybe better quality path. And then we need to force traffic using a different path. Thus, we need to use additional tools, sometimes referred as a controller, which could have a wider view and takes into considerations parameters we are interested in. Therefore, this tool should calculate different paths and somehow program it to the network. Many service providers have learned traffic engineering is hard. Influencing traffic destined to another AS is harder. Doing that in internet scale is even harder. Well, we have multiple solutions we can use, starting with the BGP typical toolset, policy-based routing, or RSVP-TE. But today I would like to focus on the segment routing. And segment routing is great. It is using a simplified MPLS paradigm, already proven in a high-scale service provider networks. traffic engineering is also greatly simplified. All nodes have globally unique labels assigned. Thus, you need just to provide stack of the labels with the list of the nodes you want to traverse through. Then you throw such frame to the segment routing network and job is done. Label stack will be processed in hop by hop, removing a top labels till a frame reached its final destination. As a kind of a byproduct of easy traffic engineering, segment routing also provides a fast sub 50 millisecond protection with the TI LFA. All those functions are currently available in our R, R2, and R3 family. Coming back to our network, I would like to examine two options how segment routing path could be pushed to our headend. It is segment routing with BGP LU and BGP SRTE. And then I would like to present a short use case, how it could be deployed in a real network. Starting with the simple case, BGP label unicast. It is enabled in the BGP process with using a dedicated address family. After that, we can receive a BGP updates containing prefix and SR path as a network layer reachability information. Thus, after programming our routing table and FIB, for every packet destined to the 222, to this prefix, we are adding a label stack and, well, job's done. Although, because it is assigned, the SR path is assigned per prefix, it is not really a practical for high internet scale where we have hundreds of thousands prefixes. So let's examine another approach with the BGP SRTE. It is a draft describing how to assign SR path not to specific prefix, but rather to group of prefixes meeting a specific criteria or policy. This policy is described as a color, which is in fact extended community attached to the BGP advertisement. BGP SRTE is enabled using yet another dedicated address family under the BGP process. So let's look better. So it definitely is better for the high internet scale. So let's maybe look how the use case could look like. And high-level mechanism is, well, pretty simple. First, you need to color your network, then feed the controller with the valid information, and finally create your tunnel. Color your network. In this step, we are basically assigning policies which then will be used by traffic engineering. How it could be done? Well, the sky or our imagination is the limit. In this slide, though, I'm showing a super simple example where prefix 222 originating from ASZ gets a different color assigned depending what is the transit AS number. When it goes through the upper C, it's a red case, it gets a color ending with a 24, while going through B, it gets 23. Well, it is super simple to add extended community. And So creating such policy on any BGP speaker is a piece of cake. Finally, as it's shown in the CLI output on the node A, it says the prefix 222 with the two different colors. And well, without any additional intervention, it is using a BGP rules and encouraged actually in this case by the higher local preference. So well, it's a natural best path. So we are selecting transit B, transit A as B. If from any reasons we want to push traffic through C, controller should generate and push a valid SR path pointing to the right node and interface. Again, keep in mind pushing traffic to the right node and right interface is important. Basically, leaving no choice, no IP routing checking at the target node. In order to construct such SR path, controller should know all the labels, including node labels and adjacent interfaces labels. Well, we all know networks are dynamic. Sometimes interfaces or node goes down. Thus, we cannot statically program our policy. We need to feed our controller with the network state information. And well, as usually in networking, we have multiple options. In our case, BGP link state extension could be used as really an efficient vehicle for updating controller with such information. BGP LS is delivering topology information, including nodes and links and their labels. And well, it is enabled with yet another dedicated address family under the BGP process. Coming back to our headend node. After controller has sent the BGP SRTE update, we can check what we finally received in the SRTE policy. As we can see in the CLI output, it's pretty simple. For prefixes with the red color policy here and here, we shall use a SR path specified here and here. So, and well, the last step is basically to implement SRTE policy in our routing table and program FIB and finish tunnel. Please forgive me about this CLI output. It was collected actually for slightly different topology without this node. So we do not have a label assigned to the node, but just labeled to the adjacent interface. But I just wanted to show that tunnel and SR policy is visible in the routing table. To summarize, segment routing with BGP-LS and BGP-SRTE offers an elegant and scalable solution for traffic engineering inside the AS and controlling traffic on our AS egress side. You may ask, is how real it is, right? And yeah, it is. This functionality was tested and verified in the multi-vendor interoperability test at ENTC in Berlin this year, 2020. Well, just before COVID-19 shut down. And Well, I had a privilege to test it personally. In this setup, Nokia was acting as a controller, Juniper as a DO2, and Arista 7280SR2 gets actually the hardest job as a DO2-1, being ahead end of the SR tunnel. So that concludes my part. I really encourage you to check the ENTC white paper for more details. So I'm now giving the floor to David.
Thank you very much. So the next quick example I'd like to showcase here is BGP flow specification, or flow spec, and how we might use that in an interesting use case. So if we take a look on the next slide here, we can use an example where flow spec can be used to mitigate against distributed denial of service attacks, or DDoS. And so the idea as a service provider, if we are receiving a DDoS attack, well, firstly, we need to be able to detect that that attack is happening. And then we have a combination of inbound traffic, typically, that is comprised of both legitimate and non-legitimate traffic. So we need some mechanism of filtering or cleaning that traffic, ideally. And because of the increased bandwidth and the high cost of that, we ideally want to perform that as close to our edge as possible. So really with that, we need the ability to identify malicious traffic in a granular way, and we want some flexibility on the traffic processing. So the idea behind BGP flow spec in this use case is the BGP flow spec address family and protocol is a standards-based way of achieving this. And so firstly, we can have some sort of controller, and this could be a third-party solution, such as in the example I will show, Netscout's Arbor platform, but of course many other platforms are available. A controller can monitor that traffic, and if it were to detect an attack, it can then program flow spec rules on Arista EOS devices. Those rules can be to match a certain type of traffic flow. So we might be matching on, say, destination IP or prefixes or given flows, so tuples of information. And those flows can then be programmed into the EOS device with some sort of desired action. So that action could be, for example, just simply to drop the traffic, or it could be to rate limit, it could be to mark for quality of service, or it could be to redirect. And so using redirect, let's say into a different VRF, we could then redirect certain types of traffic and certain flows to a scrubber or threat mitigation solution, and that scrubber can then send us back the clean traffic. Now this is supported today on the 7280 7500R family, where we support up to 24,000 entries v4 or v6, and these entries crucially can be installed hitlessly because of course the flow spec controller will want to install these entries dynamically in real time. So let's look at a very quick demo of how this is achieved. So if we go to the next slide, there's a small video demo that we prepared earlier. So if we go back to the previous slides, and the idea, as you can see here, is we have my small service provider network here, where I have a number of customers, and on a provider edge node, I have configured here the BGP flow spec address family. And so we've activated our peer, which is, in this case, the threat mitigation solution from Arbor. We can see here's our inbound traffic using a number of full internet table prefixes. We do have a negotiated BGP flow spec session with threat mitigation service. However, we're currently not receiving any routes, any flow spec rules today. However, what we can do now, this is in a steady state, we can modify this After verifying the steady state of bandwidth, we can actually simulate an attack by using a traffic generator here. And this generator is sending some attack traffic, which the threat mitigation solution can detect. And then once it's detected that, using flow analysis, it can program these rules we can see here instantaneously. So very quickly, we've dynamically installed these rules. And in this case, these rules are redirect rules. So they are matching on given prefixes, given destination prefixes here. And then we are redirecting that traffic, as you can see here, out on Ethernet 23 to the threat mitigation solution. Once we've done that redirect, the TMS, the threat mitigation solution, can perform scrubbing, that is removing the malicious or unwanted traffic, and then returning back to us here, as you can see on Ethernet 6, to the clean traffic. That was a very quick example, but hopefully that was another useful use case for you. And now, in the interest of time, I will hand over to Florian.
Thanks, Dave. Yeah, I would like to also talk about a next-gen Internet Exchange Point architecture. Next slide, please. So what is an IXP actually? Some of you might be familiar with them. They sit at the heart of the internet and enable interconnection between multiple autonomous systems. IXP provides only interconnection for ASs, so it is not an end user service they're offering. And an IXP, this is probably most important, should not inject another AS like a transit provider would do, or otherwise interfere with the traffic. Next slide, please. So let's have a bit of a look into the IX itself. What kind of services is it providing? What are you usually seeing out there in the wild for such an important platform? You usually have the peering service, which is a VLAN. All of the members are participating in a shared IP network, essentially. So depending on the size of the IXP, just one big VLAN where there is a /24/23/22, something like that. Every member gets allocated an IP address, and based on that service, the participants can then just negotiate peering sessions or BGP sessions with each other, exchange routes, and therefore improve the flow of their traffic. Several IXPs also offer value-added services as the platform's already there. It's usually point-to-point services and also using the reseller capabilities of the platform, which means the IX is reselling the services over a third party, probably even outside of their own metro, leveraging the network of the third party provider. So the reseller has one big port or multiple big ports towards the internet exchange, and then is slicing it up into smaller bandwidth services, like a 100 gig port into n times 1 gig, n times 10 gig, or even just 100 meg services. Next slide, please. So how could a next-gen IXP fabric look like? Well, first of all, it should be built on open standards. Usually IXP fabrics were always supposed to be completely replaced once there was an upgrade, once there was a new technology out there. This is supposed to be changed, make it more reliable, more future-proof. So therefore, we're only using open standards here, like moving towards inside of the metro to transmission of 400 gig ZR, for example, instead of proprietary DWDM solutions. Use EVPN for signaling, which is proven to be vendor interoperability. Use transports like VXLAN or MPLS. Be flexible up to your needs. Use automation-wise APIs or OpenConfig. It should be easy to operate and troubleshoot. Use something like BGP unnumbered with IPv6 for your point-to-point links inside of the fabric, and leverage eCMP so all paths can be active at the same time. Of course, the fabric should be cost effective as well, because the transfer price keeps dropping and dropping. And the fabric should be able to adopt new technologies and trends like Yaro showed earlier on with the segment routing with traffic engineering, without just ripping and replacing hardware inside of the IX. Next slide, please. So the peering service, what is important for it? It has to be a very reliable and lossless service, because you don't know what traffic flows over it. It can be web traffic, it can be video traffic. So we would leverage the VOQ-based architecture of the 70 to 80 here, as well as the debuffers the systems offer. We want to protect the fabric itself against misbehaving participants. So we need layer 2 and layer 3 ACLs on the customer ports, as well as the ability to configure stomp control. We don't want to have any broadcast or less broadcast in this network, because with, let's say, 2, 3, 4, 500 connected end systems, there might be some ARP traffic, there might be some broadcast. We want to keep that as low as possible, and therefore we use up suppression. We want to detect also and mitigate link and device failures as quickly as possible, so we can leverage technologies like fast reroute and BGP, prefix independent convergence. Next slide, please. For point-to-point services, we also have multiple various options. We can use VLANs just via VXLAN with Q&Q capabilities, or VLAN-based or port-based LDP pseudowires. Or even if it is an EVPN fabric, use E-line services with EVPN VPWS. This is all needed so you can create some kind of metro connectivity over your own platform for various of your participants. Next slide, please. And last but not least, as I mentioned it earlier, the reseller functionality, which is probably the most difficult one for most exchanges as of today. As I said before, it's the termination of the peering service of multiple participants on one single link. So this is realized with layer 2 sub-interfaces towards the reseller and VLAN rewriting, because the VLANs which actually go towards the reseller are completely different, obviously, as the ones we use for the platform itself. The remote participants should also be able to talk to each other. This is achieved with a feature called hairpinning. And last but not least, we should be able to maintain the commercial constraints on a per participant level. So if someone bought a gigabit service, we should shape it down and polish it to a gigabit service, so he's not able to transmit more and probably impact other customers on the same link. Next slide, please. So to quickly sum it up, Arista here has a big advantage. With using the Arista R series, you're getting full flexibility on various architectures, transport options, control plane options, API, whatever you want. And it has been proven to be reliable. There are several deployments at the heart of the internet all over the world, serving you and your customers. It's easy to extend your fabric based on the IXP growth without replacing chassis. You can just throw in another switch depending on the technology you need. You need more 10 gig ports, you need more 100 gig ports, or even you need more 400 gig ports. Also, you see a consistent feature set from 1 gig up to 400 gig, and all features I just stated are available as of today. Also, Arista invests quite heavily into IXP requirements. We talk a lot with our existing customers, and we work closely with the EuroIX community to give the IXPs the features to make the internet better. Next slide, please. Therefore, I hope we were able to show you some interesting use cases today. I would very much like to thank you for your time, also on behalf of my colleagues Jaroslav and David. The recording will be available on our within the next few days, and you will receive an email about it. And therefore, I wish you all a very nice day. Goodbye.